quickly. Today we're looking at probability distribution. I think in the previous class, we look at the last chapter of describing data, where we look at the variability in data, explaining variability in the data sets, using measures of dispersion, as well as describing the shape of the distribution using measures such as the measure of skewness, okay, the Pearson's first coefficient of skewness, second coefficient of skewness that we talked about, the kurtosis of the data today. And I think we also started, we did a rough introduction to the concept of probability. So we want to proceed from there. Now, when we talk about probability, like we said in class, is the chance that an event will occur, okay? And we said in class that for an event to occur, then first there has to be an experiment, okay? So an experiment is a process which generates outcome, okay? So experiments are processes which generates what? Outcome, okay? So an experiment like the weather forecast, we will be examining the weather forecast, okay? And the results of the weather forecast could be a sunny day or a rainy day. Okay, so the possible outcomes of the weather condition could be what? Sunny or rainy. Okay, so that will be our experiment. Now, the set of all possible outcomes of the experiment is referred to as a sample space. Okay, and it's usually denoted using capital S or using omega. Okay, so in the case of the weather forecast, we can have our set of possible outcomes being what? Being S is the set of what? Sunny day. Okay, so we can say sunny or a rainy day. Okay, so there are two possibilities when modeling the weather forecast. Okay, good. But elsewhere we can have what? We can have sunny, we can have rainy, we can have a snowy day, we can even have a cloudy day. You understand? So that is also another possibility, set of possible outcomes of that experiment. Then again, we could also have the experiment of rolling a die for our Ludo game. Okay, the possibilities are going to be 1 to 6. Okay, so in such an experiment, we are going to have S or omega to be what? 1, 2, 3, 4, 5, and 6. Okay, very good. Now, so we are saying that the set of all possible outcomes is referred to as what? The sample space, and each element or each member, okay, in the sample space, or each element in there is referred to as the element or the member or a sample point of the sample space. Okay, another experiment is the toss of two coins, like we are seeing here in this example. Okay, so if we toss two coins, then there are two possibilities that the first coin will be a head and the second will be a head. The first might be a head, the second could be a tail, the first could be a tail, the second could be a head, the first could be what? A tail, and the second could also be a what? A tail. So that forms our set omega or capital S. Okay, very good. Yeah, so that is what we said from class last week. Now let's proceed. Okay, so the next thing we talked about was the concept of an event. Okay, and we said that it is a set of possible outcomes of interest to us in an experiment. So we will be interested in the event of observing an even number in the roll of a die. Okay, so that becomes a set E, which is 2, 4, and 6. Okay, good. The same way, we may be interested in the event of observing what? At least one head. At least one head means one or more heads. Okay, So if the sample space omega was in the toss of two coins, that would be head, 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 tail, okay, tail, head, tail, head, and what? And tail, okay, tail, tail. Then these are the possible events: two heads, one head, one head. So it means that our event E, okay, is going to be the sets H, H, T, and then TH. And we also define that the probability of an event E written as P of E, or sometimes we write probability of the event E, okay? But a common notation is to use P of E, okay? It's defined as the number of outcomes in that event, okay, over the number of outcomes in the sample space, okay? So that gives us the probability of the event. Okay, so very well. Yeah, let's continue. So we said that in class last week. We want to continue from there. Yeah. So the next thing we are looking at is the properties, okay, or the axioms of probability. Now, the first thing we have to say is that the probability of an event always lies between 0 and 1. That is the first property we have to know. So the probability of an event, okay, or the probability of events, all events, okay, is always between 0 and 1. Okay, so P of X, the probability function, is always between 0 and 1. That is the first axiom we have to understand. Okay, axiom 1. Then property 2, that the sum of all probabilities, we'll see that later in the slide. So the sum of all probabilities, okay, of the various events in the mutually exclusive events in the sample space or from the experiment is always equal to what? 1. When we add up all the probabilities, we are going to get what? 1. Okay. So in very simple terms, if the possibility from the weather forecast are sunny days and rainy days, if that is the only two possibilities from that experiment, then it means that the probability of a sunny day plus the probability of a rainy day will always be equal to what? 1. Okay. And that is what we are saying here. Very good. Now let's proceed. Okay. Then again, the probability of an event, okay, is also equal to, or better still, we say the probability of an event, okay, A plus the probability of not A, okay, or A complement, is always equal to 1. So if this is the case, in the case of weather forecast, this A will be sunny. So not sunny will be what? Will be rainy. You understand? So the probability of a sunny day plus the probability of a rainy day would have been 1. So if you want the probability of a sunny day to be 1 minus the probability of a rainy day. So in that regard, then we're also saying that the probability of A plus the probability of A complement equals to 1, which means that the probability of an event A is simply equal to 1 minus the probability of A complement, okay? Or A complement just means not A. not A. Very good. So you take note of this rule too. Okay. P of A is equal to 1 minus the probability of A complement. So please take note of that. Okay, very well. Let's move on to the next rule. Then the next rule for multiple events, okay, is the addition rule. Okay, so when we talk about the addition rule, then we are talking about let me just cite an example. So a rainy, find the probability of observing a sunny or a rainy day. So anytime we use the word or, it's either sunny or rainy day. Okay, anytime we talk about or, which is also the union, represented using the union, okay, then we are talking about the addition rule. Okay, so anytime we are finding the probability of the union of events, then we are talking about what? The addition rule. And the addition rule says if you have events A and B, also A or B, and you want to find the probability, then it's also represented, like I said, using the union, P of A or B. And that is expressed as P of A plus P of B minus P of A intersection what? B. Okay, so that is the formula there. P of A plus P of B minus P of A intersection B. Okay, good. Now, when we talk about, so this is the general rule, okay, addition rule. Okay, good. But there are situations where we cannot have A and B occurring at the same time. Okay, so a typical condition is you have a box, you have a red pen, or let's use balls. Okay, so 2 red balls, and then let me change the ink to green. So I have 3 green balls. Okay, and I ask you to find the probability, okay, of observing what? So find the probability of selecting a red ball or a green ball. Okay, when it happens like that, your definition, your formula will be what? P of R plus P of, okay, G, okay, minus P of what? R intersection G. Now, let's try to reason it out. P of R will be what? Our definition, number of events. So number of R over what? The number in the sample space. Okay. I had the same thing with what? P of G is number over green, okay, over the number in the sample space. Now let's come to the third term. P of R and G. Is there any ball in this basket which is red and at the same time green? Yes, can I get some answers?
No, sir.
No, sir.
Yes. So
No, sir.
yes.
They are only red and green balls.
Yes. So we say that the ball we have here are mutually exclusive. Okay. They cannot be red and green at the same time.
Same time. Okay.
So anytime you have events which cannot be 2 at the same time, okay, we say they are mutually what? Exclusive events. So in this case, this last term here does not make sense. It is absolutely 0, okay, because that probability is not possible. So in the case,
No, there's no such.
yes. So in the case where our events are mutually exclusive, then we can clearly see that the formula comes down to just these 2. The formula will reduce to these first 2 terms here because the probability of R intersection green is 0. It's not possible. Okay. But all the same, let's solve this example since it's an example on the board. So n of r is r are 2. Okay, so 2
3.
over 5.
5. Yeah.
And 5 in the box. Plus green is what? 3
3
over
over
what?
5.
Over 5.
Over 5.
Okay. So when you find this one, this is going to give us 5 over what? 5
10.
over 5, which is what? Equal to what? 1.
One.
You
One.
understand? Why is it 1? We said per the second axiom of probability that the sum of probability of all the mutually exclusive events in an experiment will be equal to 1. Now you are looking at for the probability of red and green. And these are the only events, these are the only mutually exclusive events within the box. They're only red and green. So which means that if you are looking for red or green, then virtually you are looking at all mutually exclusive events, which are the red and green. So when you sum them, you should get what? 1. That is why we are getting 1 in this what? Example here. Okay, but the key thing you have to take note of is when events, 2 or more events are mutually exclusive, the third term in the addition rule goes to what? 0. Okay, so it is left with what? Just the first 2 terms in the formula. So that is a key thing you have to take note of. Now let's go on to any question. If you have any question, you can raise your hand. If not, I'm moving to the next. Okay.
Hello, sir.
Okay, very well.
Hello, sir.
Yes.
Just Godfrey, I just want to know, probably the balls in the basket, this one we have red and green.
Yeah.
Assuming we have different colors, assuming blue or maybe black in addition, with one, you are going to maintain the same formula to do it, or how are you going to go about it, that one?
If you had more than
2 colors.
Yes. Colors, yes.
So it depends on the question. 1. So let me say that, let me add, if I had yellow here, okay?
Okay.
And I'm asking you to find still the same question, okay?
Yes.
Then the formula remains the same. You understand? The formula will remain the same. But here, the denominator is not going to be 5 because there are now 7 ball, and this will also be what? 7.
7.
Yes. So which means at the end of the day, we'll get 5 over 7. And we are not getting 1 because they are not the only mutually exclusive events in the experiment.
Okay. I think the yellow will be 2. To be 2
yes,
over
the yellow
7.
is 2.
The yellow.
Yes.
Yeah, the yellow also will be 2 over 7.
Yes, but you've not been asked for yellow. Where the question is still
find it.
Yes.
Okay, so assuming you have been asked to find
green.
the yellow.
Yes, you've not been asked to find yellow. You've been asked to find red or green.
Okay,
so you stick to the question.
Okay, sir.
Yeah, Kinder, go ahead.
That means that in this case,
yes,
the R intersection G will be working. It will not be 0.
It will not work. It still means that selecting a ball that is red and green, that is not possible.
Okay. Okay.
It's still mutually exclusive.
Okay. But sir, please, would there be a possibility whereby you'll be asked to find R or green or yellow?
Yes, there's a possibility.
So in case of something like that, how do you go about it?
Let's do that as let's extend that to another class. Okay.
Okay.
Good. Yeah. Okay, so moving on. Let me clear. Okay. So we have another example here. I think let me skip this example, okay? Because the lights are actually off here. I don't know if the course rep informed you. The lights were off, so The system too has been on for a long time. Okay, now let's move on to the concept of conditional probability. When we talk about conditional probability, before I even explain, you see, we always have the if clause. So it will rain, given that it has already rained yesterday. Or let me say that you pass an exam, given that you have studied. Anytime we make such statements, we are doing a conditional statement. Okay. So in this case, I'm getting feedback. Please mute your microphones for me. Yeah. So anytime there are two events, A and B, and this time B has already occurred. Okay. B has occurred. So we are saying that when we write this, we say that it is the probability of A, given that B has occurred. This is referred to as given that, or if, given that, such that. Okay, so this is that, given that. Please mute your microphones for me. We don't have much time. Okay. So A given B is the probability of the event A, given that the occurrence B has what? Taken place. Okay. The occurrence B has taken place. I'm stressing on it because somebody is likely to come and say, but A happens before B. So why are we saying that B has already taken place before A? This is not alphabets we are talking about. We are saying that there is a certain event B which took place before what? A. Okay. So anytime we are writing the conditional probability of A, given that B has occurred, is defined as the probability of A and so and is referred to as intersection, whilst or is referred to as union. So A and B over the probability of B. Okay. So the probability of A and B over the probability of what? B. Okay. So if that is the case, then we can also write that the probability of B and A, I hope you can see this one here clearly, that the probability of B given A has occurred is also denoted as the probability of B and A given over the probability of A. Okay. So basically, we can also write, if we do cross multiplication, if we cross multiply, okay, then it means that this P of B will come here, okay, which will give us P of what? B here, okay, times this one, whilst at this point, it will go away. I hope you are following. Okay, so if we do cross multiplication, this is how it will look like. So the formula will now become what? I'll clean it and then rewrite again. So the formula will now become what? From this expression, then it means that we can write a statement like P, oh, I'm changing the color. Okay. So we can write a statement like P of A given B, okay, is equal times, oh, sorry, times P of B, okay, is equal to P of A intersection B. Good. So this is a statement we can deduce, okay, from this conditional probability here. If that is the case, there are also conditions where A does not depend on B, okay? There are conditions where A does not necessarily depend on what? On B, okay? So for example, if there are two people going to write examination, okay, and then let's say B is the first person who wrote the, let's say B is Ben, Ben wrote his exams first and passed the examination. And you are being asked to find the probability of A is Abraham, okay? So the probability that Abraham will pass the exams, given that Ben has passed the exams. I mean, clearly we know that Abraham's performance in exams does not depend on Ben's performance in exams, because they are two independent people, and they are writing it independent of each other. You see, so in that case, this probability of A giving B, which we are seeing in this term here, is just the probability of Abraham, because Abraham does not depend on what? On Benjamin. Okay, so then the formula will just reduce. This becomes P of A. The first term will become P of A times P of what? Of B. Okay, which will become what? P of A intersection B. So that is the term we have written here. So which means that if you want the probability of Abraham and Benjamin, okay, which is A intersection B, this time the word is and, not or, okay? So the probability of joint events, A and B, it's equals to the probability of A times the probability of B, okay? Here is A times probability of B, because A does not depend on what? B. So what we are saying here is the general rule is if you want the probability of A intersection B, it is supposed to have been from conditional probability. It's supposed to have been probability of A given B times the probability of B. But in certain conditions where A and B are independent of each other, okay? In conditions where A and B are independent of each other, then the probability of A and B is just the probability of A times the probability of B, okay? So in independent events, then the probability of the joint event A intersection B is just the product of their respective what? Probabilities, which can also be extended. Okay, but first, let's take an example to demonstrate what we have just said. So we have an example here, which will help us to understand the concept of independence. And then thereafter, we also look at the conditional probability, which we looked at. So here we have three balls in the box 1, 2, 3. And we are being asked to find the probability. Okay, first it says case 1, draw with replacement of the ball. Okay, the second ball is independent. Okay, so if we are selecting two balls, we've been asked to find the probability of E1, selecting the first ball, okay, and the second ball being event 2. Okay, good. But we are drawing with what? With replacements. If we are drawing with replacement, then it means that when we select E1, which is the first ball, okay, E1 is 1/3. The probability of E1, P of E1 is 1/3. We can all see from, okay, Then because we are replacing the ball before we select the second one, when we select, we put P1 back into the box. So it means that we will still have 3 balls before we select E2, event 2. Okay, so the probability of E2 also becomes what? Becomes 1/3. So that will also be what? 1/3. Okay, so now you can see that we have, if you want the probability of E1 and E2, it is just the probability of the first event, which is 1/3 times 1/3. And that is the probability of E1. Okay, 1/3 is the probability of E1. Similarly, 1/3 here in the second event is also the probability of E2. So we can clearly see that in the case of replacement, where the second event does not depend on the first event, okay, then the probability of their joint event is just the product of their individual what? Probabilities. That is proved from this word experiment. Now let's see the other side, the other case, okay? So in the case where this time we are not replacing, okay, we are drawing without replacement, how will it look like? So let me use a different color. When I select the first one, the probability will be what? 1/3 here. Then because I've selected the first one, this ball is no more in the box. So when I'm selecting the second ball, okay, it's going to be 1/2. 1/2 is 1/6. And clearly we can see that this 1/3 is the probability of E1. But 1/2 is not the probability of E2. And the probability of E2, like we found earlier, is 1/3. You understand? So it's telling you that the probability of the second event, so the probability of the second event depends on the first ball that was what? Taken out of the box. Because the moment the first ball was taken out, the total number of sample points in the box or number of balls in the box reduced to what? 2. So it affected the probability of the second event that was what? Withdrawn from the box. So we can see a dependency case in that word, experiment. Okay, so that is the typical example of how dependence and independence come to play, okay, in determining what the probability of the joint event of what? The joint events of several mutually exclusive events. Good. Let's go to example 2. My battery is running down a bit. In fact, it's almost out, but let's see how far we can go. Yeah, so we have the next example here. This time we are talking about a conditional probability, how to find it. Okay, so if you are asked to find a conditional probability, like we said, the given that B has already occurred, then the conditional probability of event A given B is defined as the probability of A intersection B over the probability of what? The prior distribution, which is P of B. Okay, so we are going to do both with replacement and without what? Replacement. So with replacement, this formula becomes what? P of E1 given E2 per our formula here. So this becomes E1 and given what? E2 has occurred. So in the formula, it will reduce to what? P of E1 intersection P of E2 over P of what? E2. Okay. And we all know that the various probabilities were written initially. We have them here. Okay. So P of A1, because we are redrawing with replacements, anytime we are using replacements, then it means we have independence. If we have independence, then the probability of the joint event is just the product of their probability. So it will be 1/3 times 1/3, like we found in the previous slide. Okay. Then divided by the probability of each, which will be 1/3. And when we do that simplification, you get the total probability to be 1/3. Then in the case of drawing without replacement, in the case of without replacement, there is dependency. You see, there will be dependency. So you take note of that. That will give us what? So in the case of dependency, E1 intersection E2 is not exactly the product of their independent what? Probabilities. It will be what? The probability of E1 times the probability of E2 given that E1 has occurred, which we found as what? 1/2. Okay, all divided by the probability of E2, which is 1/3. So that should give us 1/2 in the case of the dependent, okay, scenario. Let me take one or two questions. So one or two questions from the class. Let me take one or two questions from class. Yeah, any questions? Any questions, class? Yes. So my battery, yes. Before that, my battery is almost run out. Please listen, my battery is almost run
Sir,
out.
please, the network is no good at all.
Oh,
Hello, sir.
yeah. Hello, I'm listening.
Hello, sir. Please, can you please go over drawing without replacement of the balls? Please, can you go over that section?
Okay, so because of the network.
It's actually raining, drizzling at all the time.
The network is very bad. It's freezing.
Oh.